There's a water heater on this roof with no pump, no burner, no heating element, and no wires. Nothing inside it moves. By late afternoon, it's holding a tank of water so hot that the plumbing code makes you cool it back down before it's allowed to touch your skin. It's called a Thermosiphon passive water heater. 2 boxes and 2 pipes, a collector, a tank, and a loop of water that pumps itself. Now, here's the part that looks wrong. The storage tank sits above the collector. Every water heater you've ever owned puts the heat at the bottom, under the tank. This build flips that, and that one backwards-looking decision is the entire engine. Get it right, and it circulates on its own, for as long as the sun comes up. Get it wrong, and your tank quietly throws the whole day's heat back into the night sky. I'll show you exactly why. By the end, you'll understand how water pumps itself uphill, how to size this with pencil and paper math, and the 3 safety devices the code will not let you skip. Most people come at solar hot water from 2 directions, and both have a trap. The first crowd buys an active system: collector, pump, controller, sensors, antifreeze loop. Now you own a pump that runs on electricity, and a system that stops making hot water the moment the grid goes down. You bought solar to get away from the meter, and the pump plugged you right back into it. The second crowd goes primitive: a coil of black garden hose on the shed roof, 1 lukewarm rinse by mid-afternoon, and the first hard frost splits it open. That's not a system, that's a science fair demo. And there's a third failure hiding under both: people who build a proper collector and a proper tank, then put the tank below the collector, because that's where a tank looks like it belongs. Then at night, the loop runs in reverse, and the tank's heat drains backwards out of the system. If placement never seemed like it should matter, you're not slow. You just haven't seen the physics yet. Walk the water through it once. Cold water comes in from your supply line and fills the storage tank. The tank is mounted high and insulated hard because it has no heater to lean on overnight. From the bottom of the tank, where the coolest, heaviest water settles, a pipe called the downcomer runs downhill to the low edge of the solar collector. The collector is a shallow glazed box on the sunny side of the roof, a dark absorber plate with water channels through it, tilted to face the sun. Water enters at the bottom corner cool, warms as it climbs the channels, and leaves the top corner hot. From that top corner, the riser pipe carries the heated water up into the upper portion of the tank. That's the whole loop: tank bottom, down, through the collector, up, tank top. On the tank sits a temperature and pressure relief valve. On the hot outlet sits a thermostatic mixing valve. Downstream, your existing water heater stays in line as backup for cloudy weeks. One sentence: the sun makes the water in the collector lighter than the water in the tank, and gravity does the rest, all day, every day for free. Everything hangs on one fact: hot water is lighter than cold water. As water heats up, its density drops. Picture a beach ball held underwater in a pool. The heavier water shoves the lighter ball to the surface. The water in your sunlit collector is the beach ball. That imbalance creates real pressure. Engineers call it head. Raise a column of water 3 meters, and you've got 3 meters of water pressure behind it. But be honest about the scale. The density difference is slight, so the driving pressure in this loop is tiny. That makes friction your enemy. A skinny pipe can stall the whole machine. Doubling the pipe diameter cuts the friction pressure drop by a factor of about 27. So the design rules write themselves: fat pipes, short runs, smooth bores, a continuous rise with no dips. The loop turns slowly and silently, no motor needed. The collector? A glazed flat plate collector is the workhorse. Absorber plate, water channels, glass cover, insulated box. The label that matters is a listing to ICC 900 divided by SRCC 300. By listed, glazed, and rated for potable pressure. The tank, it has to be pressure rated because it lives on your house's water pressure, typically rated around 125 psi working pressure, with a dedicated port for the relief valve. Check the rating plate, not the paint job. The pipe, temperature rating is everything. CPVC is rated to about 210 degrees Fahrenheit. Regular PVC is only rated to 140. PVC never goes on the hot side. Copper runs hotter still with a smooth bore that keeps friction low. PEX varies, read the temperature rating printed on the pipe itself. For diameter, air generous, friction is the whole battle. The valves: 3 non-negotiables, a TNP relief valve to ANSI Z2122, self-closing lever style, a master thermostatic mixing valve to ASSE 1017, and a vacuum relief valve if your tank is bottom fed. One unit unlocks everything. The BTU, the energy to raise 1 pound of water 1 degree Fahrenheit. A gallon weighs 8.35 pounds, so 1 gallon, 1 degree, costs 8.35 BTUs. Supply water at 55 degrees, stored at 135, and 80 degree rise. 1 gallon, 8.35 times 80, 668 BTUs per gallon. Convert to electricity, 1 kilowatt hour equals 3,413 BTUs. So each gallon you heat costs just under 0.2 kilowatt hours. Scenario 1, light use. One person, low-flow showerhead, about 6 gallons per shower, roughly 4,000 BTUs, call it 1.2 kilowatt hours a day. Scenario 2, typical. Two people at average habits. The measured average shower is 17.2 gallons, about 34 gallons a day, around 23,000 BTUs, 6.7 kilowatt hours. Scenario 3, heavy. A family of 4 is nearly 69 gallons, about 46,000 BTUs, 13.5 kilowatt hours a day. One bath adds 24 gallons on its own. Benchmark. One national dataset puts a standard electric water heater at about 84 kilowatt hours a month. A conservative floor, busy households run well above it. Your shower math tells you where you sit. Now the overnight problem. Heat loss follows one equation. Surface area times the temperature difference between tank and air, divided by the insulation's R value. The lever you control is R. Double the R value, and the overnight temperature drop is cut exactly in half. Bigger tanks also cool slower. There's no verified rule of thumb ratio of collector area to tank gallons. Size from your BTU number and your climate, and lean oversize on the collector. Cloudy days are your safety margin. Phase 1. Structure. Before anything wet. Water weighs 8.35 pounds a gallon, so a 40-gallon tank is carrying about 334 pounds of water before you count the tank. Supports must carry the full filled weight, built to the International Building Code, braced for seismic where it applies. Never notch a rafter in a way that weakens it. And pull your permit now. A water heater or pressurized tank always requires a permit and inspection. Phase 2. Set the tank above the top edge of the collector. That's the rule the whole machine lives on. Common guidance puts the tank bottom at least 12 to 24 inches above the collector top. Wrap it in insulation like the heat is money. Phase 3. Mount the collector below the tank, facing the sun, and flash every roof penetration watertight. Phase 4. Pipe the loop. Downcomer from tank bottom to collector low inlet, riser from collector high outlet up into the tank, climbing the whole way. No humps, no sags. Insulate every foot. Phase 5. Safety hardware. The relief valve threads directly into the tank shell, its sensing element reading the top 6 inches of the tank, where the hottest water lives. Its discharge pipe runs full size, downhill by gravity, no traps, no valves, no threaded end, ending where you can see it drip, and never ever put a valve of any kind between the relief valve and the tank. Then the mixing valve goes on the hot outlet, set before the water heads for the house. Phase 6, fill it, hold pressure, call your inspection, and give it one full sunny day before you judge it. The expensive mistakes, so you recognize them. A shut-off or check valve isolated against the relief valve, that's how tanks become bombs. A trapped or downsized discharge pipe, and skipping the mixing valve because we'll just be careful. Failure 1. The night dump. Symptom: tanks hot at sunset, cold at dawn, and nothing leaked. Cause: reverse thermosiphoning. At night, the collector becomes a radiator and the circulation runs backwards. Fix: more height between collector top and tank, and insulation on both loop lines. Ignore it, and you've built a machine that heats the sky. Failure 2. The first frost burst. Symptom: a split pipe or ruptured collector channel after the season's first cold snap. Cause: water-filled lines exposed to freezing. Code says outdoor, attic, and outside wall piping must be protected with insulation or heat. Fix: protect everything exposed, and drain the collector ahead of hard freezes. Failure 3. The scald Legionella squeeze. Run the tank too hot and 140-degree water burns skin in about 5 seconds. 150 in under 2. Run it lukewarm to be safe, and you've built a Legionella incubator. The bacteria multiply fastest between 80 and 122 degrees. The way out of the squeeze is both valves doing their jobs. Store hot, 140 or more, and temper down to 120 or less at the fixtures through the mixing valve. Here's what the code actually demands: a permit and inspections. Rough in and final, full stop. The solar side conforms to the International Mechanical Code and ICC 900 divided by SRCC 300, and nothing may compromise the potable supply's cross-connection protection. The relief valve rules are absolute. A TNP valve to ANSI Z21.22 on the tank, one on each vessel if heater and solar tank are separate. Temperature no higher than 2010, pressure no higher than 150 psi or the tank's rating, sensing the top 6 inches. No valve between it and the tank. Discharge piping full size, gravity flow, untrapped, unthreaded, visible. And the temperature rules: a master mixing valve to ASSE 1017 at the source, with fixtures limited to 120 degrees. This video is educational and not professional electrical, plumbing, or structural advice. Codes vary by location and change over time. Have your plan checked by a licensed professional and your local code office before you build. I'm not going to quote you a parts total I can't verify. Collector, tank, valves, and pipe prices move, so price them locally before you commit. What I can verify, water heating runs about 9% of a typical household's electricity, around 84 kilowatt hours a month on a standard electric tank. Payback is simple division. Build cost over yearly savings, and a well-placed passive system can carry 80 to 100% of your hot water load with essentially no maintenance. And once this tank is on the roof, you've got the backbone for the next build, a rainwater catchment system that can feed this same tank. On screen one more time. Educational only. Verify against your local code. Build it once. Understand it forever. Subscribe if you want the rest of your homestead explained the same way.